Hi everybody and welcome to a new video in the audio signal processing for machine learning series. This time we'll pick up where we left last time, where we talked about Fourier transform and arrived at the point where we said, well, we need to know about complex numbers for moving forward and understand Fourier transform even better than just like the intuition level. So this time we'll look into the fundamental concepts behind complex numbers, and all of this information is going to be very useful for you to understand the deeper concepts behind audio signal processing. But before we get started, I want to remind you once again about the Sound of the Eye Slack community, which is a community with people interested in all things AI music, audio, and audio signal processing. So you can go there, hang out with very interesting people, and network with them, ask for feedback, and just share your ideas. So if you're interested and you're not signed up yet, just go check out the sign up link to the workspace, Slack workspace in the description below. But now let's move on to the topic of today's video, the complex numbers. So why should we bother with complex numbers in the first place? Well, aren't real numbers good enough? Well, it turns out that when we are dealing with the Fourier transform, if you remember from my previous video, we usually get a couple of parameters for each of the pure tones, pure frequencies that we decompose a complex sound into. And these two parameters are the magnitude and phase. Now, magnitude is a real number, and if we are just interested into looking at the magnitude spectrum of a complex sound, well, we really don't need complex numbers at all. But if we are interested to have like a deeper understanding of the full Fourier transform, and we want to factor in also the phase, now we have a problem. And that's because we don't have a compact way of dealing with these two parameters at once, so magnitude and phase. And so wouldn't it be wonderful if we had something that we could use to deal in a handy way, both with magnitude and phase, with both of these like parameters at once? Well, it turns out that we have that math can provide it with that, and it's complicated. It's not really complicated numbers. Well, it could be complicated, the topic in itself, but it's not complicated numbers. It's actually complex numbers. And as I said, this topic can be a little bit complicated, but I'll try to make it as easy and accessible as possible for you in today's video. Okay, so what's the genesis of complex numbers? So why do we need them? Well, for a long time, mathematicians have been scared of a very simple thing, and that's square root of -1, or more in general, the square root of negative numbers. So with real numbers, there's no way we can solve like this very simple thing, like the square root of a negative number. So basically, math is broken in terms of like real numbers if we want to deal with these type of things. So how do we deal with these guys? Well, mathematicians are quite creative people, sometimes quite nuts, and they came out with something completely made up, and it was so made up that they called it the imaginary units, the famous I symbol. And I has the wonderful property that when it is squared, it is equal to -1. So now all of a sudden we have a way of working with square roots with negative arguments using complex numbers. Isn't that fantastic? Yeah, I guess you bet that's fantastic. Now, this may feel somewhat like cheating or like weird, and in a sense it is, but I can assure you that complex numbers work for real. And for example, in audio processing, in signal processing, they are used ubiquitously. So now let's just get familiar with the definition of a complex number, or like just see a complex number, even if it's just like a generic complex number for the time being. So we define it as C, which is equal to A plus I times B. Now, A and B are both real numbers, and this I is the imaginary unit, right? And so the cool thing about this, it's like that this complex number can be divided into like two parts. The real part that provides us information about the real domain of this complex number, and the so-called imaginary part that provides us information about the imaginary part. Now, given mathematicians love visualizing stuff quite a lot, so they thought that we could just take these complex numbers and put them on a plane, because if you think of this, the real part and imaginary part as two separate axes, why don't you put them on a plane? And that's what they do. And so they can end up plotting complex numbers onto the complex plane. So in the complex plane, the x-axis is the real axis, whereas the y-axis is the imaginary axis. Now, let's try to pinpoint a complex number. For example, this 3 plus 2i. So for that, basically, both 3 and 2 can be thought of as Cartesian coordinates. So 3 is the Cartesian coordinate for the x-axis, for the real part, and it's over here, and then 2 is the Cartesian coordinate for the imaginary axis. And so when we just connect these 2 points, these 2 coordinates, we get like this point over here, which is 3 plus 2i. Now here we have another example, which is minus 1 plus 4i, and as you can see, we go down to minus 1 on the real axis and 4i on the imaginary axis, and here we have this point. Okay, so this is like all good and well, but now we are interested in another way of representing complex numbers using the so-called polar coordinates. And now you'll see why this is like very handy for us in the context of audio signal processing. Okay, so here, for moving from the Cartesian coordinate representation onto the polar representation, we need a couple of parameters. The first of which is this absolute value of c, which visually represents the distance of the complex number from the origin. And visually you can say it like as a red line here. Now, this is one parameter that we need. The second parameter is the angle called gamma. So what's gamma? Well, gamma is the angle between the positive real axis and the line that connects the origin with the complex number. So in other words, it's this angle over here. Now, the moment we have these two parameters, we can move easily from the Cartesian coordinate representation to the polar coordinate representation. But before we do that, we need to calculate both absolute value of c and gamma. Let's start with absolute value of c. And here we can use like some very basic math, something that probably you've done like in high school, if not elementary school. So here I just like rewrote this and added like these colored lines for clarity. So the purple line here is A, here we have B, which is represented by this yellow line, and obviously we have the hypotenuse of this triangle, which is absolute value of C. Now, as you can see, this is a right-angled triangle because we have a right angle here, and given we know A, given we know B, because these are like this is like the real coordinate for the real part A, and B is the coordinate for the imaginary part of the number, then we can easily get the hypotenuse of this triangle by using Pythagorean theorem here. And so you should be familiar with this, but basically if we square the absolute value of c, this is equal to a squared plus b squared. Now we're not interested in the square of absolute value of c, so we want to take the absolute value of c, so we have to square, well, we have to use the square root, sorry, and apply that to a squared plus b squared. So this way we can easily get, the absolute value of C. Great. So what about the gamma value, the gamma angle? So now for calculating that, we need to brush off on some trigonometry. So basic cosine and sine functions. Okay, so let's get started. So here, the cosine of gamma is equal to this side A divided by the hypotenuse absolute value of C. And the sine of gamma is equal to B divided by the hypotenuse of this triangle, once again, the absolute value of C. Okay, now we are interested in gamma. So we want to get gamma and get rid of this absolute value of C. So how can we do that? Well, we can, for example, divide the sine with the cosine of gamma and then obviously divide this guy by this guy. And if we do so, we end up with this formula here. So we have sine of gamma divided by cosine of gamma, which is equal to B divided by A. And the absolute value of C has been cancelled out, right? Now, if you are familiar with trigonometry, I'm sure you've recognized that this sine divided by cosine is indeed the tangent of gamma. Now, obviously, we're not interested in the tangent of gamma. We're interested in gamma. So how do we get gamma? Well, we need to apply the inverse function of the tangent to B divided by A. And in other words, what we do to get gamma, we have to apply the arctangent to B divided by A. Good. So this way we can get gamma, or the gamma angle directly from the Cartesian coordinates. So now I'll store this couple of parameters here, and this is like the way we can get both the angle gamma and the absolute value C starting from the Cartesian coordinates and information about A and B. That's great, but we haven't learned yet about the polar coordinates. So now, how do we move to polar coordinates? Well, once again, we have to go back to some trigonometry. And here, so you see that the side A is equal to the hypotenuse, the absolute value of C, multiplied by the cosine of gamma, and it's this guy here. And then B, the side B, is equal to the hypotenuse multiplied by the sine of gamma. Right. Now, here we have the Cartesian representation of a complex number. So what we can do next is get A and substitute A with this formula over here, because it's the same thing as we've seen, and then substitute B with this other formula here. And so here basically we are getting rid of the Cartesian coordinates A and B, and we are using instead the absolute value C and gamma, which is our angle. So if we do that substitution, we end up with this nice formula down here, which is a complex number C in polar coordinates can be expressed as the absolute value of that number multiplied by cosine of gamma plus I times sine gamma. Nice. Okay, so but now you may be wondering, well, we are doing all of this like mental gymnastics and mathematical gymnastics, but how does this apply to our Fourier transform? Well, I'm not going to give you like the mapping, the one-to-one mapping here, because you need to know more about complex numbers, but I want to give you a little bit of a hint. So with the Fourier transform, we are dealing with sine waves, right? And here you have a hint that still we're dealing with cosine and sines. So that is somewhat like close in a sense, right? And so that is a little hint that perhaps this representation can be useful for the Fourier transform. But more than that, with the Fourier transform, when we decompose a sound into a single frequency, pure tone, well, we get two values, an absolute value and an angle, a phase, right? And the hint here is that the magnitude can be somewhat mapped onto the absolute value here and the phase onto this gamma angle. So now probably you start to see here what's happening, right? So we have all of these different elements, and like both in the Fourier transform and here in this the polar coordinate representation of complex numbers, and they somewhat align. And that's great, and we can use this to our own advantage to make sense of the Fourier transform with complex numbers. But this is not today's topic. We aren't done yet with complex numbers though. So there are a few other concepts that we'll use and that are super useful for representing in a nicer, handy way our Fourier transform. So let's just take a look at them. So one of this is the Euler formula. Basically, what we are looking at here is e to the I times gamma, which is equal to cosine of gamma plus I sine gamma. Now, if you're wondering about e, this is the base of the natural logarithm. Now, this is like a very, very nice formula, and it's kind of like similar to what we are looking at our polar representation of the complex numbers. But let's try to visualize and understand what this is on a plot, what this exponential is on a plot. And so as you can see here, so what this exponential does, it basically traces the unit circle. So what's the unit circle? It's the circle that has a radius 1, and it traces it counterclockwise. And in order to like just trace the circle, what we do is we just increase the angle gamma. The Euler formula is going to be very useful to rewrite our polar coordinates for the complex numbers. But before we get there, I want to take a little detour to show you one of the jewels in mathematics, and that's the Euler identity. So mathematicians, physicists, even engineers look at this formula and they say, well, it's wonderful, it's just perfect. So let's take a look at this. So it's e to the I times pi plus 1 is equal to 0. So why is it so wonderful? Well, because it has all the fundamental elements of mathematics and symbols. It has 0, it has 1, it has pi, which is so omnipresent in mathematics. It has I, this made up imaginary unit, and it has e. So this is just wonderful. But for this to work, we need for this exponential, right, to be equal to -1. So let's check out, or let's see like if this actually is the case. Let's start from the Euler formula here. And here we can see that so if we plug pi into like this formula, we'll see that cosine of pi is equal to -1 plus I times sine of pi, and sine of pi is equal to 0. In other words, we are adding up -1 plus I times 0, which is 0. So all of this guy gives us back -1. So it checks out. That's great. But let's try to visualize this and see if it works. And for that, we should go back to the complex plane. And now we want to see e to the I times pi, and that is at this point here. So it's basically the value that we are tracing on the unit circle is the one that is resting on the negative real axis. And so this is equal to -1. And again, visually it checks out. So Euler, you are a great man, and you were right. By the way, this chap is Leonhard Euler, one of the most brilliant mathematicians to ever live on planet Earth. Okay, but now let's go back to our polar coordinates for the complex numbers. Okay. So the top equation here gives us the polar coordinates as we've come to know them. And here we have the Euler formula. Do you notice something interesting there that we could use to our advantage? Well, yes. So this guy here is basically our exponential here. So what we can do is take this exponential and plug it in here. right? And so we can rewrite our polar coordinates like this. So a complex number c is equal to the absolute value of c times e to the I times gamma. Great. So isn't this wonderful? It's wonderful because it's a very, very compact way of indicating, representing a complex number. So obviously here we have two parts of this complex number. So we obviously have the exponential and we have the absolute value. Now, the last exercise that I want to do today is to just visualize what these two components contribute to the overall complex number in a visual way. Now, this is a suggestion for you guys. So if you're learning some math or anything, really, even like in engineering, I really suggest you to go deep and try to visualize all of this with like formulas and things, because that is going to give you like such an understanding, a deep understanding, and it's going to go well beyond just like memorizing like a formula without really understanding what's going on there. And this is what I'm trying to do like with my videos in general, and yeah, and this like formula in particular right now. But yeah, without like further ado, let me just jump into this because it's so wonderful. So this exponential component, we already know it's the basically like traces the unit circle in the complex plane counterclockwise. And so what this component gives us to the complex number is the direction of a number in the complex plane on the unit circle. And here we have it. For example, this is like for gamma, which is equal to pi divided by 4. In other words, for 45 degrees, right? Now, if we change gamma and we go to gamma equal to pi, well, we're just changing the direction of the number, which now rests on the negative real axis. Now, if we change gamma once again, we change the direction. For example, at minus pi divided by 2, we are resting on the negative imaginary axis, and the value of our exponential here is going to be equal to minus I, so minus the imaginary unit. Okay, so you get the idea of what this exponential does to our number. It just gives it the direction. Then what about absolute value of c? Well, this acts as a scalar. It basically scales the distance from the origin of our number. So if we start with the unit, so basically the absolute value of c is equal to 1, well, we are just resting on the unit circle, obviously. But if the absolute value of c was equal to 2, for example, well, what would happen is that we double the distance of the number from the origin, but we stay on the same line, on the same direction. But when I say that the absolute value c, so this component is a scalar, it can obviously stretch things, but it can also shrink them. So if we had, for example, c equal to 0.5, what we would get is half the distance from the origin calculated with respect to the unit circle over here. That's great. So yeah, this is like so fascinating, like, and interesting, and I think like it's going to be like very useful moving forward. Definitely it's going to be very useful to like understand how to map the Fourier transform onto like the complex representation. And now once again, I want to give you a hint into that. So now we have a very complex way of representing complex numbers, and we are going to be using this absolute value as a way of mapping our magnitude that we have like in our Fourier transform, and we're going to be using this exponential and specifically this gamma to talk about the phase that we get out of a Fourier transform for a given pure tone. And so this is the type of like kind of like mental exercise that we'll use in the next video, where we are actually going to put into place all of the knowledge that we've acquired today about complex numbers in order to create a complex representation of the Fourier transform. And you'll be delighted by that, because it's going to look like so wonderful and so simple. Good. So this was like a quite intense video, I feel, but I hope like you've enjoyed it, because now you should have a good understanding, an operational understanding of complex numbers, their representation in Cartesian coordinates, in polar coordinates, the Euler formula, the exponential, and all of these like nice things here. So yeah, that's it for today. I hope you've enjoyed the video. If that's the case, please remember to leave a like. And if you haven't subscribed, please consider doing so. And as usual, if you have any questions, please leave them in the comment section below. I'll try to answer to those. And I guess that's it. I'll see you next time. Cheers.